Take a look, please. Okay, yesterday, we were looking at some new derivative. I gave you some new derivative rules. I will give you a sheet with these, and I'll post it online like tomorrow, because we're going to add two today. Okay. Yeah, and then those are, and I think we'll do. This is an unbelievable deal for you guys. At some point here in the fairly near future, we're going to do a derivative quiz, which is just memorizing derivatives. And I'll give you a test grade for it, which is unbelievable. That you would just have to memorize a few things and get a calculus test grade for that. But yeah. Okay, so anyway, we're looking at these new derivative rules, and we ran up against a roadblock, and that is what happens when we have a product, and how do we differentiate the product of two functions. And so we need to derive a new rule for that. Now, how does this work? If we're trying to derive something that's completely general, we have to start with something completely general. So anytime we have a product of functions, which could be f of x and g of x, you can't get more general than that. P of x is some function defined as a product function, which is just f of x times g of x. If we can come up with kind of a formula, right? We can come up with a derivative rule or a pattern based on just that. It'll apply to any product of functions, right? So how do we go about doing that? This is a great look at some proof. If you're going to go on and do any math in college, you're probably going to do a little bit more proof. And so it's good to see some of this stuff. We started this yesterday, right? We're just using our basic definition of a derivative. We know, and remind me what that is. If I want to take the derivative of f of x, just in general, what is the derivative of f of x? The limit of f of x plus h minus f of x over as h goes to 0. Exactly. And so we did that for our function p of x, right? P prime of x is the limit of p of x plus h, which would be f of x plus h times g of x plus h, minus p of x, which is just f of x times g of x, right? All over h as h goes to 0. Okay, here's where things get a little wonky, though. There's a step in a proof like this that you're not at all used to. 99, maybe 0.9% of the time, when we want to manipulate something algebraically, we multiply by 1. We multiply the top and the bottom by the same thing. Very seldom do we get to do something like this. Do we get to add 0? But we're going to add 0 here. We're going to add 0. Notice I'm subtracting the same term that I'm adding in red. So I have added 0, right? 0 is the additive identity. I haven't changed anything. Okay? We are. And then we're going to factor by grouping. Exactly. So now, and there's the motivation. That gives us 4 terms. And if I factor these in a clever way, I'm going to be able to see a pattern come out of this. What do you think I could do here? How do you think I could group these things in a way that makes sense? Like factor by grouping. What were you going to do there? What do you think, Bill? Okay, so take the first 2 terms. What could you factor out of the first 2 terms? Each of the first 2 terms has 2 factors, right? What are the 2 factors in the first term? F of x plus h and g of x plus h. Well, what's the common factor in the first 2 terms? F of x plus h. We could undistribute that. How about the second 2 terms? What could I undistribute? G of x. Okay, let's try that. Okay, and I kind of color-coded these. So I guess the green group is going to be green. The first group is green, second group is purple. Out of the first group, we factored out an f of x plus h. Out of the purple group, we factored out a g of x. Okay, why might that be useful? What does this look like? We already know that looks like g prime of x, don't we? Right, agreed? The limit of g of x plus h minus g of x over h as h goes to 0. Isn't that whole thing right here, this whole guy right here, isn't that just g prime of x? That is the derivative definition. What's this? Yeah, that's f prime of x. Okay, then now this is starting to look a little bit better. I get f of x plus h. What happened to that? Something's... Oh, never mind. I know what happened. Okay, I got to take this. What's going on? Okay, wait, that's, you can't, I don't know why you can't see the f, but they're supposed to be, yeah, they're supposed to be f of x plus h times g prime of x, right? That's g prime of x plus g of x, the limit of g of, well, let's take these limits. What is the limit of f of x plus h as h goes to 0? F of x. The limit of this difference quotient as h goes to 0 is g of x, right? Is there supposed to be, I feel like there's something else here that's supposed to be able to get rid of. I guess not. Anyway, that's g prime of x plus, everybody see this is the plus sign that connects them? That's connecting the two terms, right? The limit of g of x as h approaches 0 is what? G of x. There's no h's to even evaluate, right? And then you already told me that's an f prime of x. Well, there's my answer. That is the product rule. The derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. You see the pattern? You're always going to take the product of those two factors, but each one gets its own turn at being a derivative, right? Okay? So that's the product rule. And here it is. This is kind of a clumsy way of saying it. To me, this one is visually just kind of messy, right? The derivative of the product of f of x and g of x is f of x times g prime of x plus g of x times f prime of x. A better way to say this stuff, and the way usually it's written, at least I strongly prefer, is let's make the notation cleaner by defining u as a function of x and v as a different function of x. So whenever you see u's and v's in calculus, rarely are those individual variables. Those are almost always meant to represent functions of x, right? So look how much cleaner that looks then. The derivative with respect to x of the product of u and v, where u and v are just functions of x, is just uv prime plus vu prime. Way, way simpler and easier way to write it, okay? And we could extend the product rule, and you can kind of see what the pattern is. If I'm taking the derivative of a product of three factors, well then look what happens. I just keep getting the product of u times v times w, where one of those three factors is primed in each case, right? So uvw prime plus uv prime w plus u prime vw. And you could do the same thing with 4. You just get 4 terms if you're differentiating a product of 4 factors and so on. So let's try this. Now we can go back and do this derivative. What's our u and what's our v in this case? Yeah, right? Exactly. So what's y prime going to be then? So y prime equals what? The derivative. Why don't you real quick tell me again, what is the derivative with respect to x of uv? Yeah, uv prime. How are they connected? Plus v u prime. Okay? So then this is going to give us x times, what's the derivative of e to the x? Remember what it was from yesterday? That was the weird one. E to the x. Plus e to the x, what's the derivative of x? So there's our answer. It's just x e to the x plus e to the x. That's our derivative. How about that? That's the function that will predict the slope of that function, this complicated function. Okay, so then I'm going to show you the quotient rule. I'm not going to derive the quotient rule for you. I figure one proof's probably enough for today. but it's very similar. So again, if we're taking the derivative of a quotient of functions, f of x over g of x, here's kind of the complicated way of writing it. But write it in terms of u's and v's. The derivative with respect to x of u over v is v u prime minus u v prime over v squared. Now, how do you remember that? Here's the phrase, here's how people remember this. Low d high minus high d low. That's what goes on top. Because notice that on the top, now this is not a sum, it's a difference. And so you can't commute those two terms. It's wrong if you get this backwards because we're subtracting instead of adding. With the product rule, it makes no difference. uv prime plus vu prime, so you can say it backwards. It doesn't matter. You're adding the two terms, and two terms are commutative under addition, right? It doesn't matter the order in which you add things, but it does matter the order in which you subtract things. So it's vu prime minus uv prime. The way I always remembered it, I always thought of it as vdu minus udv, and so it kind of sounds like video. So that's how I always remembered it. This is probably a better way. This is the way. Low d high minus high d low. What's that mean? U is the high function, v is the low function. So we do the low function times the derivative of the high function minus the high function times the derivative of the low function. So low d high minus high d low. Everybody say that. Low d high minus high d low. There you go. That's it. All divided by. On the bottom, it's just whatever the low function is squared. Okay? So there's our quotient rule. So let's try a quotient rule problem. So what do we get? Here's our y. What's y prime? Low d high. So what's low? What's d high? Right, derivative of 2 goes to 0. So low d high minus, what's high?
5x minus 2.
D low?
2x.
Divided by?
X squared plus 1.
Yeah.
How do you say that?
Quantity. X squared plus 1, quantity squared. There you go. Okay, that's our answer. Of course, we would need to simplify this, but simplifying it's just pretty basic algebra. We just distribute the 5, distribute the 2x, collect like terms, and what do we get? 5x squared plus 5. What do I get on the other side? Plus 4x. All over the quantity x squared plus 1 squared. Do we want to factor out or expand out the bottom? What do you think? Do we want to expand out the bottom? No, we don't. We want to leave things factored. You'll see why. But we want to leave things factored. So then on the top, if we combine like terms, we just get negative 5x squared plus 4x plus 5. Does that factor, let's see, negative 20, does not. Doesn't factor. So that's our answer. Okay, that's it. Okay. Okay, let's try another one. Talk me through this.
Is there like a low high high to low song like there was?
No, not that I know of. You guys could make one though.
Yes, we should make one.
Okay, so low D high, right? There's low.
2x.
Mason, what's D high? We're doing our derivative quotient rule here. So low D high, what's D high? What's the derivative of 2e to the x? What's the derivative of e to the x? Okay, so the derivative of 2e to the x is 2e to the x, right? Minus high D low, what's that going to be? Jaden, what's that?
2 to the x times x.
Times,
2x.
okay, divided by x squared plus 1 quantity squared, right? And then we would just, from there, I mean, all we're doing is just distributing and combining like terms, and that's that. Okay. Now on the top, yeah.
It sounds like high, low.
So when we're simplifying this, ultimately, you guys don't really understand the motivation for this yet, but you will. But we want to have everything factored, right, as much as we can. So when we're doing that, when we're cleaning up the top, does anybody see something we could do right away that might make things simpler? Being as we're trying to factor anyway, rather than distribute the 2e to the x, what could I do with it?
Factor it out.
Hey, there's a little too much talking. I feel like I'm talking over the top of people. If I were out there, I'd probably be pretty frustrated if I were trying to listen to this. So instead of distributing the 2e to the x, what should I do? Factor it out, for sure. So we get 2e to the x times what's left over. Well, x squared plus 1 minus 2x. Everybody see that? Divided by x squared plus 1 quantity squared. So then this just becomes x squared minus 2x plus 1. What does that factor into? X minus 1 quantity squared, yeah. So we could write this as 2e to the x times x minus 1 quantity squared over x squared plus 1 quantity squared. That'd be pretty clean form. Okay? You can probably start to think about why we might want to be factoring this stuff, because what are the things what are some things we've done with derivatives already even? We've kind of looked for places when we were trying to sketch what the derivative function looked like. It was convenient for us to know where the derivatives were equal to 0, right? Horizontal tangent lines. We're going to start looking for those places quite a bit. So those are going to be zeros of the numerator. So it's nice to have it factored. Where are places where the derivative is going to be undefined? If we have a fraction here, where the denominator is 0. Right, so already we can maybe start to see some preliminary motivations for why we might want to keep things factored. Okay, so now let's just do some practice rewriting stuff so we can make the derivative easier. Like with this one here, that looks like a quotient. Should I use the quotient rule? I mean, I could.
But you can make it into the power.
Yeah, we don't want to, though. The quotient rule is the messiest of all the ones we have so far. It's the easiest one to screw up, so we'd rather avoid using it if we can. There's no reason for us to use the quotient rule here, because is this a quotient of functions? No. 8 is a constant, so I just pull the 8 out front with the constant, and I treat it much more simply. I would just rewrite this as 5/8, or at least in my head, 5/8 x to the 4th, which makes it a much easier derivative. I just use the power rule. So what is the derivative then? If I differentiate that, what do I get? Yeah, good, because I'm going to bring the 4 out, right? It's going to be the same thing as 5/8 times 4x cubed, which if I simplify is just 5, whoops, that's bad color, is just 5 halves x cubed, or either 5x cubed over 2 or 5 halves x cubed, either way. Okay, make sense? Okay. Okay, how about that one? Quotient rule, thumbs up or down? Yeah, no need, right? No need. If I rewrite this, what do I do to make this really simple? Yeah, just pull the 1/6 out front times x squared plus 3x. That's easy to differentiate. What's the derivative then? Well, I'm going to leave the 1/6 out front for now, but you're right. 1/6 times 2x plus 3. If I just differentiate that polynomial term by term, and now I could redistribute the 1/6, and I just get, what, x over 3 plus 1/2. Okay? That's such a common mistake people make is they just immediately jump in and do the quotient rule. Don't do it. We could do it, but it would be hard. Think what that would look like if we did the quotient rule. Y prime would equal low times the derivative of the high minus high times the derivative of the low, which is 0, divided by the bottom squared. That's way overcomplicated, right? Okay. Okay, what about this one? Okay, looks like a quotient rule one, right? No.
No, because you can,
You
divide
take
that
root
into
3 over
your
7x.
cancel it next to each term.
There you go. Yeah, we're just going to separate this into separate fractions and just use exponent rules to reduce, to simplify each one before we differentiate. Pull the 7 out front. And then what are we left with? We're left with 3x over x, which is what? Minus 2x squared over x, which is what? Right? Way easier. Okay, differentiate that. What's that give us? Negative 3/7 times, what's the derivative of 3? 0. What's the derivative of negative 2x? Right? See what we did, Mason? We just split this up. Split that up and made 2 fractions out of it. Okay? Okay? How about that one? Quotient rule? No, what do we do?
It's next to the negative.
Ah, there you go.
The negative. You know what I meant.
What's that do? What in the world is that doing? Oh my goodness. It's probably going to crash. I better save it.